I'll be talking about spectral analysis in spectral algorithms for graph mining and analysis. So in general, if you have a network or a graph, you want to discover things about it. And there are many wonderful tools, great tools that you can use. I'll be talking about my favorite one, which is spectral algorithms. Basically, I think it's a beautiful topic, and the algorithms can be very efficient and effective. And I use the word beautiful because I'm still surprised, but see what happens if you take this graph, no matter how you input it into the computer, you can do some algebraic computations, compute two eigenvectors of the Laplacian of the graph, and then use these eigenvectors to embed the graph into the plane and see what you get. It looks very elegant. So that's why I think these algorithms are beautiful. So today, I'll be talking about a few things. I'll start with a very basic spectral partitioning algorithms. Then I will review some recent progress in algorithms for partitioning graphs. And I'll talk about some perceived weaknesses of these algorithms that are actually not weaknesses, or you can fix them. And I will talk about a more general spectral framework. So I'll just start by getting something out of the way, which is what is the Laplacian of a graph? So here's a graph, and the Laplacian matrix is basically very simple. So for every edge, you put a -1 in the corresponding entry of the matrix, and there's two parameters here. There is the number of edges and the number of vertices. So this is the Laplacian. Okay, and now I will be talking about cuts in graphs. So there's this very straightforward connection between Laplacians and cuts. So if you look at your graph and there's S and S bar, the two sets, the two partitioning in two parts, then the cut, the total number of edges that cross between S and S bar, can be expressed very easily in terms of this quadratic form. So you set a vector x to indicate the part S or the part S bar by ones and zeros, respectively. And you just take the quadratic form x transpose Lx with that vector, and that gives you the cut. So this is a very simple connection. One of the very basic and first observations about graph partitioning was the following. Well, let me define the sparsity of a cut first. So here's my graph again, and here's a possible cut. This cut gives me two sets. On the one set, I have vertices 1 and 4. There is 3 edges that cross that cut. The total number of the edges that are adjacent to S is 5. The total number of edges that are adjacent to S bar is 7. So the sparsity of this cut is 3 divided by the minimum of these two numbers, which is 3/5. So for the sparsest cut problem, I want to find a subset S of the vertices that gives a cut of minimum sparsity. I want to find S, which gives me the minimum such ratio. And I will call this phi, or the conductance. Okay? So how do we do that? This is a very obviously discrete problem. One way to solve it is to say, instead of trying to find this vector x, which is a discrete problem, I want to actually minimize this ratio. What I'm going to do instead is instead of minimizing it over the integer numbers, the 0, 1 vectors, I will minimize it over the real numbers. So now it turns out that the minimum value is equal, of this ratio, is equal to the second eigenvalue of the normalized Laplacian, which is just a small variation of the Laplacian. And the vector that actually achieves this minimum is the second eigenvector. So there's this pair, the eigenvalue and the eigenvector. So now, what happens with the eigenvalue and the eigenvector? So it turns out that, well, the eigenvalue is always smaller than 2 times the sparsest cut, the conductance phi. And that's an easy direction to solve. Now, what the non-trivial direction is that actually the conductance is always smaller than approximately the square root of the eigenvalue. Okay? So basically, we have a discrete quantity, which is the conductance, and we have the continuous quantity, which is the eigenvalue. And what this tells us, this is the Cheeger inequality. This tells us that the eigenvalue of the Laplacian, or the normalized Laplacian, reveals information about the value of the sparsest cut. And that was one of the first observations about the power of Laplacians and eigenvectors in understanding graphs. Actually, there is a little more to it. That instead of just computing the value, the eigenvalue, which is a value, you can find a so-called approximate eigenvector, which is not exactly the eigenvector, but something which approximates the eigenvector. So what you can do with the eigenvector then is sort it, and then sweep through the eigenvector and find the sparsest cut among the n possibilities that are suggested by that eigenvector. And that particular cut you find in that way actually gives you a cut which has a good, relatively small sparsity. Okay? So in other words, approximate eigenvectors can find us a cut which is not perhaps great, but it's okay. It's not bad. All right. So there is something positive, and that was the first observation, as I said. Well, what about the computation of these approximate eigenvectors? It sounds like a very difficult problem. The moment you hear the word eigenvector, some of you, I assume that you think it must be a very hard problem, something that's very difficult to compute, or at least very difficult to compute for very large graphs that we focus on here. Well, it turns out that this intuition is false. Actually, there are algorithms that have been discovered fairly recently, which are linear systems solvers for Laplacian, and based on them, eigensolvers for Laplacians, that actually can find you these approximate eigenvectors for graphs that have millions of variables, or millions of nodes. Okay? We are talking, I don't know, 50 millions in modest hardware that you can buy, with a small amount of money. So this is actually something we've done, and it's not just theory. You can download the code from my webpage. Okay. So then that's a good thing, because we have something that gives us non-trivial information about the partitioning of the graph, but also something that can be done fairly well in very large graphs. So maybe there's more to the spectral method. Well, here's a problem. Pick your favorite network, and the problem is to find k clusters. And I want the clusters to have some sort of quality associated with them, in which case I can define it to be, for example, that I want to minimize the maximum expansion. So I want basically each cluster to be relatively isolated from its neighbors. Okay? So there are many works in this topic in data mining, perhaps hundreds of papers. But what can we say about proving things, actually producing clusters that have provable properties? That was a very big open question that was answered recently in two works that are very elegant and very nice. They are also based on computing eigenvectors, approximate eigenvectors. And they do verify this conjecture that has been used or explored for a long time, that we can find very good k-way partitionings by taking the normalized Laplacian, finding k eigenvectors, and then treating these eigenvectors in order to recover the clusters. And this is a generalization of this Cheeger inequality that I showed you, in the sense that it relates the quality of the cut with the kth eigenvector, the kth eigenvalue, lambda k here. Okay. So, well, okay, we can do things fast, but it looks like we have this problem that the quality cannot be that great, because we have this Cheeger gap between the smallest possible cut that may exist in the graph, which could have value as small as the eigenvalue, but the only thing we can guarantee is something that's related to the square root of that. Okay. So then the question becomes, is the Cheeger inequality tight? Can we perhaps improve it? Maybe it's just a It's just a mathematical theorem that hasn't been worked out in detail. Maybe we can do something better. But the answer is that Cheeger inequality is tight. In other words, the guarantees that it gives us are met by actual graphs. And so the quintessential example here is that of the line graph, the path graph. Okay, it has n nodes. So the eigenvalue of that graph, the smallest one, is approximately 1 divided by n squared. And the sparsest cut in this graph is approximately 1 divided by n. So you see that square root relationship between the two quantities. And there is a Cheeger gap here. And that gap is order n. Okay? So the Cheeger inequality is tight. However, the Cheeger method is something else. The Cheeger method actually uses the eigenvector to find us a cut. Perhaps if we follow this procedure, the Cheeger method will give us the correct cut anyways. However, that can also be disproven. There are graphs for which the Cheeger method returns cuts as bad as the Cheeger inequality predicts. So we seem to be then stuck with cuts, partitionings, that are just okay. They are not as good as we could hope for. So can we do perhaps something more in special classes of graphs? Perhaps there are these counterexamples, but the counterexamples may be very special. So what happens in the case of a special class of graphs, which are the expander graphs, graphs that are very well connected, is that the eigenvalue is a constant. So for this class of graphs, the Cheeger gap is constant. So in other words, the Cheeger inequality is tight in some sense for expander graphs. So there are then two extremes, trying to analyze a very good case and a very bad case. So the good case is this complete or expander graphs, where the information we get from the Cheeger inequality is good. And there is the bad case, which is that path graph. So then an idea will be to do the following, to combine the two cases as follows. We just have T expander graphs arranged in this path fashion. Okay? So in this case, we can actually calculate and find that the sparsest cut and the eigenvalue have a Cheeger gap, which is order k, about k. So this can be a very large graph with n nodes. However, because we have these expander graphs arranged in this fashion, the Cheeger gap is going to be much better than what predicted by the classical Cheeger inequality. So maybe we are into something here. Maybe there are graphs for which we can obtain better information. And that is actually true. That there is a generalization of the Cheeger inequality that also appeared recently that tells us that the conductance is a function of lambda 2, which is the second eigenvalue, but also of lambda k, which is the kth eigenvalue. And as you can see, the square root now gets into the kth eigenvalue. So for graphs whose kth eigenvalue is large, this gives us a much better bound. And actually, these are graphs that exist in practice. For example, real network graphs have this property. The kth eigenvalue for fairly small k is constant. So, however, there's still a gap here. And so the question is that are we really stuck with just OK cuts? So here's a few reasons to be more optimistic actually about the spectral methods. So we have to remind ourselves that eigenvectors are just a tool, and what we need to find is partitionings, good cuts. Now we've talked about the algebra. We said it is tight. We cannot do much about it. We're stuck with it. We cannot fix it. However, maybe there's a possibility that we can fix the graph. And let me give you a specific example of that. Here's again the path graph, which is this is a very bad case for the Cheeger inequality. And it is over here down, right? So I'm going to construct a graph which looks like a binary tree on the top of it, okay? So it has these leaves, which correspond one-to-one to the nodes of the path graph. And inside here, I have internal nodes that follow a binary tree structure. So then I have two graphs here. I have T, which is the Laplacian of the binary tree. Then I will do, and I have the path graph. What I'm going to do with this bigger graph T, the bigger tree, is to perform a Gaussian elimination of the nodes in the interior over here. I'm just going to use Gaussian elimination in a symmetric way. And that's going to give me another matrix, which is also Laplacian, and it is, in fact, a graph, C, which is what is called the surcomplement of this tree. Okay? And it turns out that for all Lord partition S, this path graph and that surcomplement C have approximately the same cuts. However, if we look at the Cheeger gap for this graph C, this Cheeger gap is small. Okay, this is a little hard to parse right now. I'll just repeat it this way. I have my path graph. The Cheeger inequality is bad for it. What can I do with it? I cannot change the Cheeger inequality. It's tight. However, I'm going to do the following. I'm going to construct a graph. I'm claiming there is a graph whose Cheeger inequality is tight and has the same cuts with the path. In other words, I constructed another graph. I did not change my cuts too much, but I did change my eigenvalues. And in that new graph, which has the same community or cut structure as my original one, I have eigenvalues and eigenvectors that give me the right thing. And I did it here for the path, and it's actually possible with every graph. Given any graph, you can fix it. You can change it a little bit with some operations, combinatorial operations, in order for the eigenvectors and the eigenvalues to work well. And so you can find the partitioning for this new graph, the modified graph, and go back and infer things about your original graph. So this is something which is not implied by all previous improvements of the Cheeger inequality that I mentioned before. All right. So here's, going to the last part. Here's something from the abstract. We have only scratched the surface in understanding the potential of spectral methods for graph analysis. Okay. So what do I mean by that? So far, I have talked about very simple things. It's just a Laplacian or a normalized Laplacian, and I find the eigenvectors. I don't know what that noise is. Okay. So and I find the eigenvectors of the Laplacian or the normalized Laplacian. However, I can do way more general things. Given two graph Laplacians, A and B, I can define a generalized cut, a minimum generalized cut, which is this optimization problem. I want to minimize this ratio with these two quadratic forms. And so what happens here is that I have a quantity which favors small cuts in the graph A and bigger cuts in the graph B. Okay? So for example, let me take this out of the way here. Okay. So for example, I could have my graph B be a very simple case, just an edge. Okay. So what happens in that case? Then my optimization problem, this optimization problem becomes just a mean cut problem, which is a very well-studied problem. So anyways, the point here is that I may have a particular problem in data analysis or in graph analysis where I have extra prior information about my data. I can incorporate this information into the graph B. And I can pose an optimization problem and try to optimize this. I can find, again, I can do a relaxation of this problem and find the eigenvectors, generalized eigenvectors. So the main question then is, can the spectral method be extended in generalized cut problems? In other words, is there a generalized Cheeger inequality? And the answer is positive, that you can define, again, the continuous quantity, which is the eigenvalue of the pair, and you can find the generalized cut. So these two things are related. They're related in a very simple way. The simple way is that one is the conductance times just the usual conductance of A. So in other words, there are graphs or cases where this generalized Cheeger is small. Cheeger gap is small. And actually what I mentioned about the classical Cheeger inequality, the simple one, that it can be fixed. You can fix the graph so that you get a tight Cheeger inequality. This holds for the generalized problem as well. This Cheeger inequality can improve for any pair of graphs A and B, just by playing a little bit combinatorially with a graph A. So this generalized eigenvalue problems offer, in my opinion, unexplored avenues for graph analysis. So let me do a summary here of the main ideas that I went over today. First, large data is amenable to spectral algorithms. We have very fast spectral algorithms that you can use for very large data. Also, combinatorial pre-processing can fix the performance issues of the spectral algorithms, can make them run better and give you better and more accurate results. And third, there are natural ways to incorporate prior information that you have about your problem and solve generalized problems, eigenvalue problems, in order to discover more things about your graphs and your networks. So as a last slide before I leave you, you can actually find some implementations of these algorithms on my web page. There is, in particular, an implementation of finding effective resistances of graphs, which are basically some type of generalized eigenvectors. And based on this, we have we have created clustering algorithms that give much better clustering or much better communities relative to prior algorithms. And just as an example, by computing these so-called effective resistances, we were able to improve the visualization of certain graphs. So this is a real network graph where you actually feed it into a standard plotting tool and you get this. But after you actually compute these effective resistances that you can grab from my page, the code you can grab from my page, you actually visualize a graph based on these effective resistances, where you reweight your graph based on the effective resistances. You get a much better picture of the communities. And that reflects actually computation, underlying computation of communities that have much better guarantees and much better properties. And with this, I will stop and take any questions you might have. Thank you.